some of the Big Bang theory's validity is being questioned with new information. The James Webb Space Telescope has just made a surprising discovery that is revolutionizing world physics. The recent image captured by this telescope has produced persuasive arguments that have caught experts off guard, putting an end to a great deal of speculation. The most recent find made by the telescope is visually stunning and capable of changing our understanding of the universe. Experts' discussions regarding this image have revolved around the perception of the cosmos. The stunning image taken by the James Webb Space Telescope challenges our understanding of the universe. One of the issues addressed by this finding concerns primary questions in astronomy: the universe's age and its rate of growth. Researchers from various generations have been baffled by this unsolved phenomenon and have conducted numerous studies in search of answers. Cosmologists investigate how the universe originated, how it works, how it has changed over time, and how it might end. In the last 100 years, this area has seen great advancements. The most widely accepted cosmological theory is the Big Bang theory. It holds that the universe began roughly 13.8 billion years ago with a dense and extremely hot origin. To understand its expansion, scientists cite the value of the Hubble constant, which indicates the speed at which the universe is growing. But figuring out how to measure the Hubble constant is difficult. There are two primary methods: measurements of the early universe and measurements of the current universe in space. Things like stars and Type Ia supernovae, which are utilized as standard candles due to their consistent brightness, allow astronomers to determine their distance, and, as a result, compute the Hubble constant. As the universe expands over time, scientists are able to calculate the Hubble constant accordingly. There are two main approaches. One is the measurement of the early universe. Scientists use readings of the cosmic microwave background, CMB, radiation, discovered in the 1960s, as the glow left by the Big Bang. This microwave energy comes from a time when the universe existed just 380,000 years after its origin. By measuring the tiny ripples in temperature and polarization emitted by the CMB, astronomers can determine the age of the universe and its expansion rate. However, there is a problem. These methods do not yield the same result. Local measurements indicate that the universe is expanding faster than what CMB data suggests. Scientists are trying very hard to comprehend why the results differ. To unravel more mysteries of the universe, further studies are underway. The differences in measurements indicate that we do not yet understand all the signals, or that there are errors in one or both methodologies. But thanks to the James Webb Space Telescope, we can look further into the gloom of space, revealing more elements than ever before, including planets and galaxies we never thought possible. Scientists hoped the data would aid them in determining the Hubble constant. But the first wave of data has revealed unexpected findings that don't align with current expectations. Could this information give us new insight into space? We may need to rethink how we understand the universe. We could discover forces and particles never seen before. Or we may find that dark energy, the unknown force accelerating the expansion of the universe, needs to be reconsidered. With each new discovery, our ideas about space evolve. For instance, the cosmic microwave background radiation discovered in 1965 was strong proof of the Big Bang theory. Prior to that, scientists believed the universe would last forever, expanding at a constant rate indefinitely. However, new evidence showed this was not the case. In the late 1990s, it was discovered that the speed of the universe's expansion was increasing. Scientists also discovered dark energy and began exploring its impact. Every time we learn something new, we test how well it fits with what we already know and develop new ways of understanding the universe. Without this process, the challenges we face in cosmology could not lead to better understanding. This issue is not only complicated but also exciting, because it drives us to develop better tools to explore space. Scientists around the world are interested in this cosmological puzzle because everyone wants to learn more about the universe. Most importantly, it demonstrates how science is always changing as we learn new things. Another concept that goes hand in hand with Hubble tension is the idea of tension in space, which refers to how matter is distributed throughout the universe. We use this information to model the universe's structure and examine how it has evolved over time. Some areas of space have many galaxies clustered together, while others are relatively empty. Scientists use different methods to determine the magnitude of this dispersion. One possible way to address this is to examine how distinct densities of matter, such as galaxy clusters, bend light from distant galaxies. This phenomenon, known as gravitational lensing, allows us to see the effects of dark matter, which does not emit light and is therefore undetectable. Scientists also analyze the cosmic microwave background, CMB, radiation, the Big Bang's afterglow. This light has traveled for about 13.8 billion years, carrying information from the early universe. By studying the CMB, scientists can understand how the universe was full of irregularities when it formed. However, this data does not match the wide-ranging irregularities observed in the current universe, the non-spherical distribution of gravity. This discrepancy between the early universe's uniformity and the complex, uneven structure of the present-day cosmos poses one of the biggest challenges in modern cosmology. Scientists are striving to understand how the universe evolved from a nearly homogeneous state into one with vast galaxy clusters, voids, and intricate web-like structures of matter. Some experts propose that unknown physical processes may have influenced the formation and distribution of matter. Others speculate that existing models of gravity or the behavior of dark matter may need refinement. These uncertainties have led to the development of alternative cosmological models, including modifications to general relativity and new interpretations of quantum field behavior in the early universe. Furthermore, the concept of cosmic inflation, a rapid expansion of the universe in the first fractions of a second after the Big Bang, remains a topic of intense study. While inflation explains the large-scale structure and uniformity of the CMB, it also raises new questions. What caused inflation? What mechanism ended it? And could it be linked to the mysterious dark energy driving current acceleration? As telescopes like the James Webb continue to peer deeper into the cosmos, they provide snapshots of the universe at various stages of its history. These observations may help reconcile the conflicting measurements of the Hubble constant and provide clarity on whether new physics is required. Another significant development is the increasing precision of measurements in gravitational wave astronomy. The detection of ripples in spacetime caused by colliding black holes and neutron stars opens a new observational window into the cosmos. These events offer additional tools to measure cosmic distances and expansion, potentially providing an independent check on Hubble constant values. Meanwhile, new missions and experiments, such as the European Space Agency's Euclid telescope and the upcoming Nancy Grace Roman Space Telescope, aim to map the distribution of galaxies and dark matter with unprecedented detail. These efforts could shed light on the nature of dark energy and the tension between different cosmological observations. Ultimately, the pursuit of these questions illustrates the evolving and self-correcting nature of science. With each anomaly and each contradiction, scientists refine their models and seek more accurate explanations. The current debates about the universe's expansion, composition, and structure reflect not failure, but progress, the relentless drive to uncover the fundamental workings of reality. As we stand on the threshold of new discoveries, one truth becomes clear: our understanding of the universe is still in its infancy. The James Webb Space Telescope and future observatories are not just tools, they are keys unlocking the hidden chapters of a cosmic story still being written. The text suggests that matter in the early universe was more uniform than it is now. Viewed through the lens of gravity, this implies that something fundamental is missing in our interpretation, bringing us back to the mystery of dark matter and how it operates. According to Rice, he and his team were able to use the Webb, which allowed them to rethink their work. They used the Space Telescope to examine whether a potential error in the Hubble Space Telescope's measurements could be the cause of this discrepancy. However, the JWST showed the same deviations, which is worrying. Between these two observations, Rice said, "Somewhere, our understanding of the universe must have a fundamental flaw." In an interview with an astronomical magazine in the United States, Rice stated that the new space telescope has made it possible to look deeper into the universe through its sharp infrared view and to study cosmic distances with ever greater precision. Both dark matter and dark energy are mysterious components that make up a significant part of the universe, but their nature remains elusive. While black holes have been the leading explanation for certain gravitational effects, there is increasing interest in determining how dark matter and dark energy might influence these cosmic events. Permit me to know your opinion in the comments box. If you liked the video, remember to like and subscribe. Thank you so much for watching, and I'll see you in the next one. Thank you. As scientists continue to analyze the James Webb Space Telescope's data, the foundations of modern cosmology are the subject of unprecedented scrutiny. The telescope's capacity to observe galaxies that are just a few 100 million years old, mere years after the Big Bang, has challenged existing models of galaxy formation. Contrary to previous beliefs, it appears that the universe hosted more mature, massive galaxies than expected. Based on these findings, either galaxy formation occurred much faster than previously believed, or our understanding of the physics governing the early universe requires a fundamental revision. One emerging theory to explain these discrepancies involves modifications to the lambda-CDM model, the current standard model of cosmology, which includes cold dark matter, CDM, and lambda, a cosmological constant illustrating dark energy. A few physicists suggest that dark energy might not be constant at all but may instead change over time or interact with dark matter in mysterious ways. This form of dynamic dark energy, sometimes referred to as quintessence, may provide an explanation for the varying rates of cosmic expansion observed at different epochs. Other researchers are looking into alternative models of gravity, such as modified Newtonian dynamics, MOND, or scalar tensor theories, which call for modifications to Einstein's general theory of relativity at cosmological scales. These theories attempt to explain phenomena like gravitational lensing and the formation of cosmic structures without invoking unknown entities like dark matter or dark energy. While controversial and not yet widely accepted, these ideas emphasize the increasing willingness of scientists to question long-held assumptions in light of new observational data. The JWST has also opened up opportunities to examine the atmospheres and chemical makeup of exoplanets, some of which orbit in the habitable zones of their stars. These studies may not directly impact our understanding of cosmological expansion, but they add valuable context about the evolution of matter, star systems, and the potential for life in the universe. Additionally, the chemical fingerprints the JWST detects in these environments may provide clues regarding the wider spread of elements in the universe, another important piece of the cosmological puzzle. As more data pours in from the James Webb Space Telescope, scientists are increasingly aware that we may be on the brink of a paradigm shift in our understanding of the cosmos. Long-standing models, once thought to explain everything from cosmic inflation to galactic evolution, are being tested, and in some cases, stretched to their limits. Among the most intriguing revelations are the telescope's observations of unexpectedly compact and luminous galaxies existing when the universe was less than 1 billion years old. Their sheer brightness and maturity suggest that either star formation occurred at rates far beyond what current models can explain or that an entirely new mechanism may be responsible for their rapid development. Some researchers propose that early dark matter structures acted as gravitational scaffolding, speeding up the assembly of galaxies. Others hypothesize that exotic physics, such as interactions between dark matter and normal matter, or the presence of yet undetected particles, might have driven accelerated evolution in the early universe. Meanwhile, precision measurements of cosmic microwave background radiation, conducted in parallel with JWST observations, reveal subtle anisotropies, tiny fluctuations that could hold the key to understanding the universe's earliest moments. If these signals can be interpreted correctly, they might provide new insights into the nature of inflation, the rapid expansion thought to have occurred fractions of a second after the Big Bang. The convergence of these studies, early galaxy formation, dark energy dynamics, exotic gravity theories, and high-precision cosmological measurements, underscores a growing consensus in the astrophysics community. We may be on the cusp of a scientific revolution. While definitive answers remain elusive, what is clear is that the universe still holds countless secrets. The James Webb Space Telescope, with its unprecedented capabilities, has opened a new chapter in humanity's quest to understand the cosmos. And as we gaze deeper into space and further back in time, we are reminded that each discovery, however small, brings us closer to answering the most profound questions of our existence.